Hello everybody. This is I don't know which one to call it. Lecture 1. I don't know. This video is going to go over vectors for the AP Physics C. These are used all the time in AP Physics, but you will never experience a problem dealing with vectors alone. Alright, so before we get into vectors, let's talk about a scalar. Scalar, and I'm kinda Khan Academy style because they're heroes. So hence the reason I'm making this videos, because Khan Academy doesn't have an AP Physics C section, so I wanted to see if I can do something about that. Alright, so a scalar is just any sort of magnitude. I don't know, whatever, like 5 pounds or 5 kilograms or 5 billion pounds. You get the point. 5 billion. About just units, anything. It's the size, whatever, millimeters, length. We call this a magnitude. Magnitude is just how much of something there is. So, for example, if I had 5 pounds of something, then the magnitude would be 5. So a vector is just a scalar, but with a direction. So in physics, 99% of the time, it's going to look something like this, like 5 meters a second east. And you're going to get used to the metric system because that's what the physics C exam is in. Alright, so here's our direction, and here's our scalar. So 5 meters a second to the east, or I could say I'm applying, let's say I have a box right here, right? And I'm pushing it with 200 newtons of force to the east, and it's not always going to be east, but I just happen to pick east again. So now, 200 newtons to the east, or to the right, it doesn't really matter. But now you get the point with the direction. So the way we're actually going to represent vectors is, let's call this vector A right here, and you would write it like that. And it doesn't matter if you write this like that, just as long as you have an arrow above it, that means it's a vector. Okay, now that we know what vectors are, let's see how we can compose them. Multiply, add, subtract, divide. Well, not really subtract, I don't know. Combining them. Let's see. Let's say I have a vector A and a vector B, right? And let's say I have vector B. So let's say vector A is this. We're not going to give it a magnitude yet. We're just going to say this is northeast, or up to the right, and this is vector B. If I wanted to add these, we use the tail to tip method, meaning we put the tip of one of these vectors and put it on the tail of the other vector, and then draw out the rest of the triangle. You'll see what I mean. So let's start with vector A, and that's the tip, my bad, the tip of vector A. Let me write it down. And then vector B. Now, this is not A plus B. This is A plus B. Get it? And it doesn't matter which one you start off with. You could put the tip of B at the tail of A. You will still get the same result. I'll prove it. So this is vector B. And then, oh, let's put it on the other side actually. Vector B. And now we have vector A. And we can see that it's still the same. I'm not the greatest artist in the world, but I'm good enough to show you that it really doesn't matter. You see? They're kind of parallel. Alright. Now, if we want to subtract vectors, the order actually matters now. Let's say I have A minus B, or vector A minus vector B. Let's do the same thing again. So, vector A and vector B. Now we're subtracting B from A. So what we do is we flip the direction of this, because remember, vectors are a direction with a magnitude, or a magnitude with a direction. And magnitude, if you forgot, it means just how much of something you have. So, let's flip this. So we're going to put negative B is equal to this. So now we can do the tail to tip method. A, in fact, negative B, A minus B. How awesome. And now I'm going to do it again the other way to show you that it really does not matter which one you start off with. Alright, so vector B, negative vector B, right here. Wait. It's going to be A. And what do you know? It's parallel. And what does that mean? They are exactly the same. How awesome is that, my dudes and gals, dudettes? Multiplying vectors are very easy. If I wanted to multiply vector A times 2, let's say this is vector A, and let's say it has a length of 1 meter. Guess what? It's going to be 2 meters. The direction does not change, unless it says change. And the same thing goes for dividing vector A divided by 2. Let's say vector A is, let's just go with 1 meter again. I forgot to put 2A right here. So then that would mean 0.5 m, little cute vector, is 0.5 meters. Alright, now let's look at vectors on a coordinate axis perspective. I don't know what to call it. So, if I have a vector, let's call it vector A again, and it's 3 units long. Units could be meters, miles, light years. It doesn't matter. If we're putting on an axis plane, instead of saying 3 units to the right, we could just say 3i with that little thingy-majig above it. So, let's see, I have 1, 2, 3. And this is going to be vector A, 3 units, or 3i. And what do you think vector B will look like if I say it's 1j? Oh yes, it is going to be 1. And that's our vector. So let's just draw it real quick. That's vector B, and that's vector A. And if we wanted to add these, what do you think we'll do? That's right, the tail to tip method. So let's do it. It says A, B, like that. So this is actually kind of weird. because this isn't what you're used to seeing. You're used to seeing something like this, where it's all one triangle, instead of something like this, where it's a deformed triangle. This is actually still correct. Yeah. Sometimes they'll say, let's say, for example, vector A is 3i plus 1j. And vector B is 2i plus 3j. I'm just picking really low numbers because I'm going to draw these out and I don't want to make the vectors go off the screen. So, here's how we actually do this. Remember, the I is our unit that's representing the horizontal axis. So it's going to be x, and j is going to be the one that's representing the vertical axis. So x, y. Now, if we wanted to add these two together, what we would actually do, remember this formula, it would be a x plus b x, which is just going to be I, plus a y plus b y, which would be j. I have no idea where people got I and j from. That nobody knows. Or maybe somebody does know, but I certainly don't, and nobody needs to know to get a perfect score or a 5 on the AP exam. So, let's do this. So 3x, which is our ax, plus bx, which is right here, I, plus ay, which is right here, plus by, which is 3j. Now, we should get 5i, almost said 4 for some reason, plus 4j. That is going to be our new vector. So, let's try and draw it out. I'm going to erase this right here. So, let's draw it. So, A is 3i plus 1j. So, 1, 2, 3, 1j. So, right there. And now we have B, which is 2i plus 3j. So 1, 2, and then 1, 2, 3. It's going to be right there. Let me label these, actually. Now, we have A plus B, which is 1, 2, 3, 4, 5. 1, 2, 3, 4. Right there. Oh, dang it. Okay, let me try it again. Oh, that is our new vector. And if you need more proof, let me does it. So, A and B. Oh, snap, son. What do you get? A plus B. Now, look at how similar they are. Just perfect. A, look at that. A is closer, like, okay, the angle for A, let's call it theta 1, is smaller than theta 2, which is going to be A plus B. And check it out, theta 3 for vector B. Let's prove it mathematically. Vector, so theta 1, and then theta 2, theta 3. Now you see up here, theta 1 is less than theta 2. Oh, snap. Okay. Um. Oh. Okay, I made a mistake. So, actually, this is going to be theta 2, and this is going to be theta 3. Theta 1 is less than theta 2. 3. Jeez. So look, theta 1 is less than theta 2, right, as it says in the picture. And theta 1 and theta 2 is less than theta 3, which proves it right here. A simpler way to describe this is, you see, this is more pointed upwards, this is more pointed to the right, and this vector is right in the middle. And let's see, vector A is pointed more to the right, vector B is pointed more upwards, and vector A plus B is right. It has both traits. We're not always going to be adding vectors or trying to find out how to draw the vector that is the result of adding or subtracting or multiplying or subtracting two vectors. Sometimes you might be asked to find the magnitude of a vector. So let's say A is 2i. Okay, 1, 2, 1, 2. And vector B is 2i. I mean, 2j, my bad, everybody. Okay, so, look at this. This is going to be vector A, and this are going to be vector B. Now, let's say I already gave you vector C, but we have to find the magnitude for it. I guarantee you, this is probably very similar to what you've already seen before. So, remember how I said it's kind of like a triangle? A, B, A plus B, and you're given the magnitude of this and this. To find this, you use the Pythagorean theorem, x squared plus y squared. So, let's find it. 2 squared plus 2 squared is equal to 4 plus 4, or square root of all of this, which is equal to the square root of 8, which is equal to approximately 2.828 units. That's the magnitude of it, not the direction. If we wanted to find the direction of a vector, it's also very simple. Now that we have all three of our side lengths, we use the three golden ratios of math. They are sine theta equals opposite over adjacent, cosine theta equals adjacent over hypotenuse, and tangent is equal to the integral of the derivative of the integral of the inverse of the derivative of your function of x and y with respect to the z-axis. No, I'm just kidding. It's just opposite over adjacent. Oh, and just so y'all know, these kind of functions do exist. They're just three-dimensional. So, let's say we could use any three of these to find this angle. Any three. It does not matter. And if you don't have one of these side lengths, but you have other two, you could use the Pythagorean theorem to figure out the last side. Real quick, if anybody doesn't know how, if you have the hypotenuse and one of the side lengths, to find the length of the other side, you take the square root of the hypotenuse and you subtract it from, let's call this, let's call the side that you already have G for given. You would use that instead of plus G. Now, let's just use the simplest one, or the one that most people are familiar with, sine. So let's use sine theta equals the opposite of this angle is 2. The hypotenuse is 2.83. And if anybody doesn't know what a hypotenuse is, it's the longest side of a triangle. Now we have our ratio, which is sine theta. We're looking for theta, not sine theta. So we have to rearrange for theta. The way we do this is not by dividing by sine. We do sine inverse over time, well, not over, times our little ratio here, which is going to be equal to about 45 degrees. How awesome. Now, if y'all are given the angle and 2 out of 3 side lengths, you could use these ratios to find the third length. However, if you are given the magnitude of only the hypotenuse and the angle, it is actually still possible to find both of these side lengths right here. All you have to do is use the trig ratios. They're going to be sine theta equals opposite over hypotenuse, and cosine theta equals adjacent over hypotenuse. So this is going to be right here. To rearrange for this is, let's just call this x and this one y. So we're actually going to use cosine. So this side right here is the side length that is adjacent or right next to this angle. This is also right next to it, but that's our hypotenuse. So we're going to say cosine theta equals adjacent over hypotenuse. So that's x over 5 cosine theta, which is what it's equal to. But we already have theta. We are looking for x. All we have to do is just rearrange for it. And the way we do this is multiply both sides by 5, cancel out, and that is our side length. So you plug this into the calculator and you get, so say this is 30 degrees. You plug this into the calculator and then you would get 4.33. Now we could use the sine ratio to calculate this side, but you could also use the Pythagorean theorem. Yeah, so let me just make a general little thingamajig here. Let's call this x, y, and z, and this is our given. So x is going to be, oh yeah, our theta. This is going to be z cosine theta, and this is going to be equal to z sine theta. Alright, so now we're going to talk about the dot product, which is something that can be used to multiply two vectors. I'm talking about something like if vector A is this and vector B is something like this, we can multiply these together. to get a scalar. And we can multiply a vector by a scalar, let's call it b, to get another vector. So remember, vector a times a vector b is going to be a scalar c. Alright, so let's go over it. If I have vector a and I have a vector b like this, there are two ways to calculate the scalar of well, the product. It's called the dot product. So let's break it down. Right. Let's call this theta b and theta a. So how we would go about doing this is we find this angle right here. Let's call this theta c. Now that we have this angle right here, we do a times b parentheses. This is very important. Times cosine of theta c. Now, make sure you have this in parentheses. This is not the same as a times b cosine theta c, and this is not the same as b times a cosine theta c. The reason for this is because we're multiplying all of a by the horizontal component of b, and this would be multiplying all of b to the whole horizontal component of vector a. But really we want to multiply the whole of vector a, the whole of vector b, times this angle right here. And the way we go about doing this, well, right here, you have the magnitude of this, and the magnitude of that, and this angle right here, and that is your scalar. That is the magnitude of the product. Magnitude. Remember this. Magnitude, magnitude, magnitude. Please remember. This is not your vector. Alright, I've said that enough. Another way of figuring this out is, let's say this is bx, by, ax, and ay. So all we have to do, or an easier way, I would say it takes longer, but it's easier. Or it's not really easier. Well, they're both easy, but anyway, the point is to find the magnitude of this thingamajig, the scalar, is ax times bx plus ay times by. There you go. So the reason we use cosine in that earlier formula is because we want to find the portion of one vector that's parallel to the other vector. So let's say the cosine theta of a is going to be parallel to this right here. Actually, let me just draw it out for you. So let's say I have this right here. Actually, I'm gonna just draw this on a other little piece thingamajig. Let me go over here. So vector A, vector B, and I just rotated the whole thing to like 90 degrees clockwise. Call this theta. So let's construct this right triangle right here. This is a cosine theta for this side of the triangle right here. Obviously, right? And you see how this portion of the triangle in between this boundary is parallel to vector B. I just wanted to I just drew it on another picture because if I did it like this, that would be pretty hard to understand. If this is pretty hard to understand, sorry, you can just roast me in the comments and I'll help you out. So remember how the dot product was all about finding the portion of one vector that is parallel to the other vector? What do you think the cross product is? The portion of one vector that is perpendicular to the other vector. So, let me demonstration. A, vector B, nah, about something like this. There you go. Vector A, vector B. So we want to find the portion of this that is perpendicular to vector B. Now, how we go about doing this is very simple. It's basically the exact same thing from before, but this is going to be A sine theta, and that's perpendicular to this. Let me just put a right angle here. Cut. Now, this is awesome. So earlier, the dot product was when we take two vectors and get a scalar, but the cross product is when we multiply two vectors to get another vector. So this right here, the cross product of this whole system right here is A times B, parentheses. I already explained why it should be in parentheses, times sine theta. Very similar to dot product, but you know, perpendicular. Now, the worst thing about the cross product is that it is three-dimensional. That's right, three-dimensional. So, let's say I have, not gonna draw it like that. I'm gonna draw it like this. Down, down, down. This is gonna be vector A, vector B, and vector C. Now remember, this is the horizontal axis, or let's just assume this is going to be on the horizontal axis. So X, Y, Z. So I take back earlier about what I said about 3D physics, but you're not going to be using 3D physics like you would with anything else except for vectors, because it is too much time. But this is the only part of the whole exam that's going to be 3D. So let's draw this right angle right here, and then this right angle right here. Now we have a three-dimensional thingamajig. Remember, this was I, this is J, and this is actually called K. How awesome. So let's say I have this angle right here. So, the magnitude of the dot product can also be found like this. The area of, let me do this in another color. Right here, this parallelogram right here, because there's an angle right here and it isn't 90. The area right here is equal to the magnitude of the cross product. Go back. We're almost at the home stretch. So remember, the dot product was ax plus bx, or ax times bx plus ay times by. Oh, son. Well, the cross product is basically the same thing, just 10 times more complicated. So let's say let me draw this out on 3D thingamajig. So this is going to be X, Y, Z. Let's say vector A is in all three dimensions. So let's say the tip of vector A is going to be at uh, let's say the tip of vector A is going to be at x, y, and z. I like to draw my z's like this, and vector B is also at x, y, and z. We could find the cross product using these coordinates. Also, just for fun, earlier I showed you this. This is how you graph a 3D function right here, because the f of x would equal like just x, right? So let's say this is, so that'd be x, right? So if it's taking into account both x and y, then it would be x and y to get z. But my favorite is x squared plus y squared, because this shape gives you a cone, kinda. This isn't related to physics at all, but I know like some of you were mad curious about this right here. This is how you draw a 3D graph. And mathematically, we could even do a f, x, y, z, but the problem is we have no idea what a fourth dimension looks like. So we can't graph it, but we can still find all the characteristics about it. This is our glorious equation for the cross product. It is the y portion of A times the z portion of B. You could do the rest. So, yeah, have fun with that. To find these magnitudes right here, you use the thetas here, the theta here, and where else? Oh yes, and a theta right there. I'm gonna call this. Actually, no, we're not gonna call it 1, 2, 3. We're gonna call it x, y. No, that's not y. That's y and z. Dang it, z. Another way to do this. Oh, there's a lot of ways to do everything, my friends. Is by matrices. So let's say A times B. Right? This is our matrix equation. Combining these thingamabobbers, you have to know how to do for matrices. So now we are at the very end of our lesson. Alright. Most of this, I guarantee you probably won't get now, especially the dot and cross product. So I'm going to make another video doing example problems for all of the material that I just covered. Yeah, so thank y'all for watching. After that, I'm going to get into kinematics, and then hopefully I'll finish up mechanics, and then we'll go into electricity and magnetism. I have a lot to do, about 34 videos, and this is 1 out of 34. Please, I don't know, share this to somebody, because I really want to help out, and hopefully if this gets popular enough, this could go on Khan Academy, which would be really cool, because Khan Academy is the reason I'm doing this. Khan Academy has helped everybody, well, not everybody, but a lot of people out substantially, so I feel like I should give back with my little map of physics. Yeah, I actually didn't erase anything from my lecture. All of this is everything that I tried to teach you today. Alright, I'm going on too long. I hope y'all have a good day. Thanks for watching.